All right, so here we're continuing our work with vectors and applying it to kind of a field of physics called kinematics, which will also come up in our calculus work. And one of the main ideas is an application of our vector equation of a line, imagining it representing some point of some object moving through space, quite often through 2 or 3-dimensional space, over time. And ideas like velocity and acceleration and speed come into play here. So let's look at this. We got some particle, some point. It's moving with a constant acceleration, which means it's speeding up or slowing down at some constant rate. At time 1, it has a velocity like this, and at time 3, it has a velocity like this. We want to find its acceleration as well as its velocity after 5 seconds. Well, one helpful thing to remember is that first acceleration is a vector. And if the acceleration is constant, we can find it by calculating our final velocity minus our initial velocity divided by the elapsed time. Because if it's a constant, it's essentially like the slope between the change in velocity. So in this case, I'm going to write my velocities in vector form. So I'm going to start with my final velocity, I guess. So my final, that's not a highlighter. Take to my final velocity was this. So I'll write that as -1/1. Take away my initial velocity was this, and I'll write that as -3/2. And all that's being divided by 2. And so if I just subtract my numerator, I get -2/1 is my column vector. Dividing by 2, same as multiplying by 1/2. So in that case, I get a vector of -1/1/2. Or going back to my components, I can write this as as +1, not -1, and -1/2. There you go. And I can write this as a component of I minus 1/2 j. And it doesn't really matter which way you write it. Just keep in mind what does matter is these have units, and this is acceleration. So in this case, units are meters per second squared. And so then I ask, okay, what's the velocity after 5 seconds? And there's more than one way of doing this. But in general, we can find the velocity at any given point by some starting point. This is like our position vector in the last question. I'll go with the time at 1 second, plus the elapsed time times the acceleration, which we now know the acceleration is 1/-1/2. And so if I want to find the velocity at 5 seconds, just keep in mind my t will not be 5 because my starting point here came from my initial velocity, which was at 1 second, not 0 seconds. So the elapsed time has been 4 seconds. Just like in the previous part, there was a 2 here because the difference between 3 and 1 is 2. So my final velocity, I can calculate by using this vector here, plus 4 times my acceleration. Because what that acceleration means is that every second, my velocity changes by the x component increases by 1, the y component decreases by 1/2. That's what's happening every second. That's what the acceleration is telling us. Every second that is occurring, because it does have a constant acceleration. And so if I do that 4 times, that tells me how my velocity has changed. And it's a relatively quick calculation, and I get exactly 1/0 meters per second, or what's the same as just a component of I meters per second, which means at that moment in time, it is moving to the right or to the east 1 unit per second, and it's not moving vertically at all, or in the y-axis, whatever this is representing. All right, so a little less abstract. Let's imagine an object being basically thrown into the air, fired into the air, in which case gravity starts to pull it down. And so we have a projectile with an initial velocity of 5/6 meters per second. So let's think what that means. That means if I have a quick little visual here, I have something being fired, or at the instant it's fired, its velocity is 5 meters horizontally and 6 meters vertically. So it's being fired on this sort of angle. As soon as it's fired, though, gravity starts to take charge and makes a projectile motion like this. And gravity is only affecting its vertical component, not the horizontal component. And so how do I find the final velocity? It's very similar to the last thing we did. The final velocity I can find by using some initial velocity plus the elapsed time times the acceleration. In this case, the initial velocity is 5/6. The elapsed time is 2 seconds. And the acceleration, the only reason this is not going up is because of gravity. And so the acceleration is gravity, which is a vertical change, and it's pulling us down. So the horizontal, there is no horizontal component to the acceleration. The vertical component is a negative 9.8. Because again, it's pulling down. And so like before, it's a relatively quick calculation, and I get a vector of 5 over negative 13.6, and the units are meters per second. But that's the velocity. It's asking for the speed, and the speed is a scalar quantity. Speed is the magnitude of the velocity. And so I need to find the length of this vector. And so the speed will be, again, the magnitude of my velocity, or in this case, the square root of these two components squared. So 5 squared plus negative 13.6 squared. Again, it's the length of the vector. And in this case, we should get about 14.5 meters per second. And so keep in mind that value there is telling you the speed in sort of one-dimensional space, for example, like that way. Whereas this is telling us the velocity, how the components are changing vertically and horizontally. I can see those components. Please remember again, speed is a scalar quantity. It doesn't have a direction. Velocity does. All right, so let's take this to three-dimensional space. And again, we'll just look at two objects. What are they? I don't know, objects. You could apply this by making them boats or planes or whatever. But they are moving in three-dimensional space. And object A has initial points like this, and it's moving at this velocity. Object B begins at this point in three-dimensional space and moves in this velocity in three-dimensional space. So we have 2 points moving, starting at different points in three-dimensional space and moving through that three-dimensional space in different directions. So we want to find an equation that represents the distance between these objects over time, and then use that to determine if these objects actually collide with one another. And if they don't collide, what's the closest they get to one another? So I want to express each of these as a vector equation, similar to what we did in previous lessons. And so for object A, I'll call this RA. And the vector can be expressed as the initial point, which was 1, 3, 0, plus, in my previous questions, this was lambda. In this case, it's the change in time times the velocity, negative 3, 4, 2. So this here represents the change in time of that first particle, point, object, whatever it is. Let's do the same thing for this. Initial point plus the change in time times its velocity. All right, so if we want to find an equation in terms of time that tells us the distance between these two, well, first, it's helpful to look at each of these equations as their individual components, x, y, and z, and see how those relate to time. So for example, for object A, its x component is the same as 1 plus negative 3 times t, or just 1 minus 3t. That's the x component. The y component is 3 plus 4t. The z component is 0, which I don't need, plus 2t. And so everything I see here, here, and here came from these components, so 1 plus t times negative 3, and so on. And do the same thing for my other object. If I do the same thing here, I get the x component comes from negative 1 plus 2t. The y component is 2 minus t. The z component is negative 3 plus 3t. And so that tells me for each of these objects, their place in time, either in terms of the x, the y, or the z. So if these two are going to collide, well, at some point in time, the x, y, and z should be the exact same for both at the same point in time. Otherwise, they're not colliding. So how can we figure that out? Well, again, one way is to find the distance between these. How can we find the distance between these? Well, really, we've seen before, it doesn't matter if it's 2 or 3-dimensional space. We apply the Pythagorean theorem, and distance can be found as the difference between the x coordinates, all squared, the difference between the y coordinates, all squared, and the difference between the z coordinates all squared. And then we square root that. And so I can say the distance will equal, I'll draw the square root later, the difference between my x coordinates, so this minus this, or really 1 minus 3t minus -1 plus 2t. Subtract those two, you get 2 minus 5t, and it's that squared. Now keep in mind, if I could subtract the other way around, we'd get 5t minus 2, which when you square it makes no difference. And plus, same thing for my y components, so subtract that minus that, and you should get 1 plus 5t all squared, and then my z components, that minus that. And you should get 3 minus t all squared. But keep in mind, the distance is the square root of all of that, right? Essentially the Pythagorean theorem applied in a three-dimensional space. So this here is a function. If we just pick any value in time, we will see their distance between one another. If at some point that distance is 0, then they've collided with one another. At some point in time, the distance between them is absolutely 0. So how can we do now? Let's graph this. And I'll go to Desmos here. And here's the graph, which I can see right away, these two objects do not collide. They never, the distance between them never reaches 0. And so I can now say they do not collide. So when are they closest? Well, let's see. They're closest when the distance is closest to 0, which is this minimum right here. And so that's when these two objects are the closest. And what do these values represent? The x coordinate, that is time. So at about 0.157 seconds, they are closest to one another. At that point, they are about 3.57 meters from one another, but that's as close as they get. So closest distance is about 3.57 meters when time is about 0.157 seconds. And so, like I said, if they had collided, we would notice that it crosses the x-axis at some point. Good, they didn't collide. No one got hurt.